Hello class, this is Adam Ward. I wanted to work with you today on an example problem where we're using our surface fluxes across, for example, in this case, a pond with a steady state inflow and steady state meteorological conditions to estimate what temperatures will be in that system. And this is of interest to us because, of course, temperature is a dominant variable when we're trying to figure out things like reaction rates in the system, when we're trying to figure out saturated concentrations for dissolved oxygen and so forth. And so in this problem, we're given several characteristics of a pond. The main objective here is find the steady state temperature. And so for our simple system, we'll start by writing out the heat balance for this problem. So on the left-hand side, we've got density times specific heat times volume, d temperature, d time. And on the right-hand side, three terms that are dealing with inflows, outflows, and fluxes across the surface. Now, because this is a steady state problem, we'll take the left-hand side and zero that out. And taking a quick inventory of what we have, we know all of the constants. We know the temperature of the inflow, the area of the lake. What we don't know is the steady state temperature, and we also don't know that capital J, the total surface fluxes. And so as we've done in class, we're going to go ahead and calculate all of those component J's and then add them up to get the overall flux across the surface. So with that approach in mind, let's go ahead and first calculate that JSN, that's the solar shortwave radiation. Basically that's the incident sunlight. And in this problem, we're given a net solar radiation of 300 calories per square centimeter per day. Given in the problem statement makes that easy. The next flux that we'll think about is atmospheric long wave radiation, sometimes called black body radiation. This is radiation of heat by things that have heat. And so we're thinking about our Stefan-Boltzmann law. And in addition to that, we're correcting for two things. One is atmospheric attenuation, and the middle term that I've shown, and the second is reflection. From class, you'll remember that we've got an attenuation constant of about 0.6. We can estimate that about 3% of that radiation is actually reflected rather than absorbed. Stefan-Boltzmann constant we're given, and so the problem here relates to this E air, or what is, what is that vapor pressure of the air. And if you look in your textbook, you're given several equations that describe this. What we're going to use is the relative humidity times 4.596 times this exponential equation that you see here. So we can go ahead and plug in the air temperatures that were given. We can calculate a vapor pressure for the air of 14.3 millimeters of mercury. And from all of that, I calculate long wave radiation being an influx or a heat load functionally of 642 calories per square centimeter per day. So those are the sources. And so at this point, we're going to go ahead and start thinking about the sinks. The term we just did is long wave radiation from the atmosphere to the stream. Of course, the stream itself has heat, so we've got radiation from the stream back to the atmosphere, JBR, back radiation. And so we can calculate that by multiplying the emissivity of water by the Stefan-Boltzmann constant, and then the water surface temperature raised to the fourth power. And you'll notice here that this term actually contains that water temperature T. If the pond is well mixed, then the temperature within it is equal to the surface temperature. And so we can't solve this one out straight away, but we can solve it at least as a function of the other unknown variable. Conduction and convection of heat in and out of the pond. And for this, we take Bowen's coefficient. That's 0.47 millimeters of mercury per degree Celsius. We multiply that by the wind speed function and then the difference between the water and air temperatures. You might remember that wind speed function is 19 plus 0.95 times the wind speed squared. And in this problem with a wind speed of 3 meters per second and that's taken as a wind speed at 7 meters above the water surface, standard measurement height, I get a wind function of 27.55. And again, that has both surface temperature and air temperature in it. So when we write out what we do know, we find that we've still got something that's got the water temperature in it again. Final heat flux we'll think about is evaporation and condensation, and we can calculate that by taking our wind function and multiplying it by the difference between the saturated vapor pressure of the air and the actual vapor pressure of the air. And you've done at least a part of this already. You've done the wind speed function of 27.55, and then as I'm drawing here in green, that saturated vapor pressure is everything except for the relative humidity term that was previously calculated. And so if you're doing this problem in the future, you might think about making sure you do that calculation separately and then scale it by relative humidity. That would save you a little bit of time and effort here. So there's our saturated vapor pressure minus our actual vapor pressure that we previously calculated. And by summing those together, and of course taking into account the directions that we've assumed, so the first two being influxes or gains of heat, and the latter three being losses of heat, you can take your heat balance equation, now with J replaced by a function of temperature, and if you go through the algebraic solution yourself, one equation, one unknown should make you happy, and you can calculate a stream temperature, or excuse me, a pond temperature of 17.3 degrees C. So that's the steady state temperature. That 10 degree inflow is going up to that steady state of 17.3. So that's a pretty substantial increase in temperature by virtue of flowing through this pond. One additional thing that may be interesting to you to do either in this problem or in subsequent problems is, now that you know what the temperature is, you can actually go through and calculate what those fluxes are for terms that previously had water temperature, such as long wave radiation and the conduction convection terms. And so if you take your idealized system, you already knew the solar shortwave was 300 calories per square centimeter per day. Atmospheric long wave you could calculate, but now you can also put magnitudes of water long wave radiation, conduction and convection, and evaporation and condensation. And those terms are all shown in calories per square centimeter per day. One additional thing that may be of interest here is to compare what that looks like for the influx and the outflux, or what's the surface doing relative to the inflows and outflows? Does the surface matter, or are we dominated by the flows? And so previously in your mass balance, you did density times specific heat times discharge times temperature for the inflow. And that gave you a heat per time. And remember that flux is a heat per time per area. And so to get this into equivalent units, you can simply go ahead and divide by the surface area of the pond. When you do that, I get an inflow of 300 calories per square centimeter per day. And you can do the same thing on the outflow and find that you're losing about 520 calories per square centimeter per day equivalent for the outflow. And so by doing this, it lets you calculate which of these terms is the most critical to getting that heat balance correct, which has the largest impact, and which are fairly negligible in this case. So as an example, the evaporation and condensation term here is representing less than 10% of those total heat fluxes. And so that may be a term, or the condensation and convection term, those may be terms you would drop, or certainly you might worry a little bit less about collecting the parameters that would be necessary to actually parameterize a model with these in the field. Thank you for sticking with me. I know this was a long video, but I hope it helps you see how to calculate all of these different kinds of heat fluxes, where they come from, and how you can use them to analyze a system. Thank you.